In this video, I'm going to build on the original video on atomic orbitals where I actually just looked at energy levels and saw how they're subdivided into sublevels. I'm then going to look at these sublevels in a bit more detail and see that they're actually all broken into things called atomic orbitals. And an orbital is just a region of space where an electron is most likely to be found. To do this, we need to know a little bit more about the electron. They're extremely small and extremely complicated things. And because they're extremely small, they don't follow classical mechanical models for the behavior of particles. It turns out they actually behave like waves, like wave functions, and particles. A bit like light. Light we know exists in waves, but also light can emit packets of energy like a photon. So this theory is called the wave-particle duality theory. And I'm not going to attempt to go into really mathematical models of quantum mechanics behind this. I'm just going to state some of the principles which allow us to talk about electrons in a way that helps us to build up the structure of an atom. So wave-particle duality means that you can get something that behaves like a particle, like a tangible thing, and also like a wave function. Some of the principles I talked about really help us to unpick the structure of an atom. And I'll start with Heisenberg's uncertainty principle. And this uncertainty principle basically tells us that we can't predict the exact position and the momentum of an electron at the same time. I.e., if an electron here, we can't say where it's going. This does make sense because we previously said that the theory about the shell of electrons was wrong. I.e., if an electron was here, we don't know that it's going to orbit a nucleus in a certain path. So we don't know the direction it's going to go or the speed it's going to go at. One thing we do know about electrons is that they do exist at a certain energy level, so they have a fixed energy. And this energy corresponds with an associated energy level that I talked about in a previous video. So without overcomplicating things, I'm going to simplify it a little bit by saying that we can come up with models that can depict roughly where an electron is going to be at any one point in time. So let's look at hydrogen and its outer shell electron. If, let's say, this is the nucleus of hydrogen, and I wanted to depict where its outer shell electron was, and I took a snapshot of where that electron was, and it was here at one point. Then if I did it again, and it was here. If I kept repeating that over and over, what I would do is build up a model of where that electron was most likely to be found. And it turns out that the region of space the electron is most likely to be found is always in this spherical manner. It looks like a circle here, but in 3D it's like a sphere. So this electron has the highest probability of being found in a region of space that looks like a sphere. And what we do is we just call that an s orbital. If I did the same for helium's outer shell electron, I would get the same distribution, or a similar distribution at least. The electron would be found around the nucleus in a spherical manner. And what we said is I call this an s orbital. Now I can do this for using quantum mechanics and mathematical models. I can do this and build up a picture about all of the electrons in different sublevels. So let's say I looked at carbon's outermost electron. I could build up a model for exactly where that electron was most likely to be found. So again, if this was the nucleus, and I took a snapshot of where that electron was most likely to be found, I would build up a picture. And that picture would slowly look like this shape. Okay, it's a more complicated shape than where hydrogen's outermost electron is to be found, but it's a very distinctive shape. Now, because this orbital looks different to that orbital, I give it a different name. And this name is called a p orbital. Now, if I look at the next element along and found a distribution for its most outer shell electron, it would also exist in a p orbital. Remember, an orbital is just a region in space where an electron is most likely to be found, and it turns out there are actually 3 p orbitals on every p sublevel. So, if I go back to my picture of energy levels, which is here, I can see that I actually did in fact have 3 orbitals at the p sublevel. And I said that it contained 3 p orbitals. Reason being, there was a jump on going from the 2s to the 2p sublevel, and I knew that there were exceptions on how the sublevels were filled according to the ionization energy, because there was exceptions in the ionization energy. So I just now have a better picture when looking at my quantum mechanical model of what an orbital, or the region of space where the electrons most likely to be found, is. Turns out the 3p orbitals that I've denoted here all look the same, but just face a different orientation. This one goes in this direction, there's another p orbital that goes at 90 degrees to that, and there's another p orbital that goes at 90 degrees to that. I'm now going to introduce an image which shows all of the types of orbital which I've mentioned in this diagram here. So this image here comes from the Chemistry Libre Tech's website, and it shows the shapes and sizes of each of the orbitals that I've listed on the right hand side of this video. The s orbital is spherical in shape, p orbital is a dumbbell shaped, and you've got 3 of them in 3 different directions. The d orbitals are more complicated, and you've got 5 of them, and the f orbitals there are down below, belonging to the lanthanides and actinides. For leaving cert specifically, you just need to know the shape of the s orbital and the shape of the p orbitals. You don't need to know the shape of the d orbitals. What I will focus on next is looking at how the orbitals are filled up on going across the periodic table. I said at the start about a couple of different principles we needed to follow. One was obviously the Heisenberg's. We couldn't determine the position and velocity of the electron at any time. The next one is the Aufbau principle, where electrons enter the lowest available energy level. Something we also need to adhere to is the exclusion principle, or Pauli's exclusion principle, where no 2 electrons can have the same 4 quantum numbers. That means something happens when electrons have to go into the same orbital. The last one being the rule of maximum multiplicity, which I talked about earlier. When orbitals of equal energy are available, then electrons try to remain unpaired. So let's start off with hydrogen. Hydrogen's electron enters the lowest available energy level, which is the 1s orbital. So this is helium. The reason they're drawn like that is because when electrons are in the same orbital, they can repel each other. Okay, but to differentiate each electron itself has what's known as a magnetic spin property. And it turns out when electrons enter the same orbital, they have opposite spin. So I represent them like this. Okay, you don't need to know too much about that, just that when you represent an electron, you do so with opposite spin. Okay, lithium's outermost electron then will go into the s orbital like that. Then beryllium's will go into the 2s orbital like that. Then we go up to the next energy level, which is where we saw our first dip in the ionization energies, because we know now that the second energy level is actually subdivided into s and p orbitals, and the p orbital is slightly higher in energy. So that's boron's electron there. Then we go across, and carbon has a choice of orbitals now. It will not go into the same one as boron. If there's orbitals of equal energy, electrons try to remain unpaired. So that's carbon. That's going to be nitrogen. Then oxygen goes into the next one like this. Turns out that was where we had another dip in ionization energy for oxygen. That's because it goes into a p orbital, which is already half full. Therefore, there's repulsion there already, so it's easier to remove. There's also added stability to a half-full sublevel, which you get when oxygen's outermost electron is removed. So then we go across, and we have fluorine entering here and neon here. Now I'm not going to go into the start of the 3s and 3p orbitals, because that's going to be sodium going all the way across to argon. They fill in the exact same way as the previous period. So the next electron we're going to consider is potassium's there. Potassium's electron actually fills an s orbital. That's because when empty, the 4s orbital is actually lower in energy than the 3d orbitals, or the 3d sublevel. And calcium's then goes into this here, also an s orbital. Then we move into scandium. That starts to fill up the 3d orbitals like that, all the way across to titanium, vanadium, chromium, and manganese. Turns out chromium is actually a bit more complicated. Chromium should go in like that, but in fact there's an extra stability associated with half-full sublevels. So chromium, actually, because the energy difference between the 4s and the 3d is so small, will have a half-full 4s, 3d, just like that. Manganese then, electron like this, then you get iron, feels like that, and so forth across the table. Turns out then, when you get to copper, copper has a chance to get a full d orbital and a half full s orbital, and that's what it will do. So in the leaving cert, it's important to be able to write out the electron configurations just using the orbitals, and I'll just go through a couple of examples for now. So if we look at potassium, for example, I know that there's 19 protons, so therefore 19 electrons. So potassium's electron configuration will look like this: 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. A little bit more complicated than the junior cert method, but that's what we get. So that's its summary. We've looked in more detail of atomic orbitals. We know that they actually are regions of space where the electrons are most likely to be found. Talked a little bit about wave-particle duality and the wave nature of electrons and how to fill up energy levels. And finally, just finishing on electron configuration.